Hello everyone and welcome to SE5055, Colloid and Surface Science or Colloid and Interface Chemistry. This then is your physical chemistry hit for the year, and we've got a lecture series this year where we're going to focus on colloidal systems and the physical chemistry of these systems. And this is a very important field in chemistry, both in terms of fundamental study of the behavior of particles and molecular aggregates in solution, but also it has huge commercial application and importance. Now, I'm going to give you a very broad introduction to colloid and interface science. You can get quite specialist even within this field. And there's going to be about, I suppose, 15 lectures all in all. We have 4 practical sessions, which will happen later on in the term. Today then, I want to introduce you to the field. I want to introduce you to what we mean by a colloid. And I would like to treat this lecture as a gentle introduction into the physical chemistry of these systems. I want to consider some of the important historical perspectives of the field. So we'll have a look at kind of where the field started. We will work up a definition of time in these colloidal systems, or how we can think about defining time from the perspective of particles that are suspended in solution. We'll go through some of the common basic definitions that we find in colloid and interface science. So these aren't, that we think about concentration in slightly different ways in colloid science. We don't always think about it in terms of moles or even mass per mil. We tend to think about it in slightly different ways. And I want to then consider what we mean by stability in colloidal systems, because you'll see as we progress throughout this lecture, when we think of the stability of a chemical system, we often frame it from the perspective of the stability of the molecules that are involved. And we're not really talking about that kind of stability in colloidal systems. We think about stability in a slightly different way, and hopefully you'll see how we think about that as we move through this lecture. So a little bit of history. The study of colloidal systems is actually very old, and I'm not sure that the people involved originally knew quite what they were studying, and it began way back in the 1840s when Francesco Celmi was looking at the aggregation of what he called pseudo-solutions in water of sulfur and silver iodide. So that already gives you a hint into the idea of colloid science. We're looking at the assembly here of sulfur and silver iodide. So a lot of the material that we'll be covering will be looking at how molecules come together and self-assemble into larger structures. We're not necessarily interested on what's going on at the individual molecular scale. If you think about our studies of inorganic chemistry, or the study that you've been conducting in organic chemistry, usually we're thinking about a molecular transformation. So we might be thinking about a reactant A plus a reactant B with a defined molecular geometry gives us product C. And we frame our approach to that by thinking about the structure of an individual molecule and how that reacts with another molecule. In colloid science, then, we're thinking about molecules coming together and self-assembling into much larger structures. So things like nanoparticles are good examples of colloidal aggregates. And the forces that hold those larger structures together are often things like hydrogen bonding or van der Waals forces, and not necessarily physical chemical bonds. Now, as a result of that, it makes these systems incredibly interesting to study, because those forces operate over far longer distances than the forces that hold a bond together, for example. So if you have a large collection of molecules that are self-assembled into a very large structure, and there are lots of van der Waals bonds and hydrogen bonds within that structure, then it can interact with other structures in solution through these forces, and they can operate over quite long ranges in solution. So Michael Faraday then developed a gold dispersion where he reduced gold, or tetrachloroaurate, HAUCl4, was reduced by sodium citrate in his experiments, and it transformed into a very deep wine red solution. And not that Faraday knew it at the time, but he'd actually synthesized one of the first samples of gold nanoparticles. And they're incredibly stable. You can still see them in the Royal Institution. So I think the original doer of gold nanoparticles that Michael Faraday synthesized are still in the Royal Institution in London, and they're still a beautiful deep wine red colour, and their colour comes from the way in which they interact with light. Far more about that later on in the module, and in one of the experiments for this module, you'll actually be synthesizing some gold nanoparticles in exactly the same way. Now, the materials that I described on the previous page are all consist of finely divided solid particles that are dispersed in an aqueous electrolyte solution. So we call these sols. And the term colloid then, I think the first recorded term of the word colloid was developed by Thomas Graham in 1861, and he took the nod from Greek, where colloid means glue. And Graham defined a colloid in terms of its inability to pass through a membrane. So that instantly tells you there that there's another aspect of colloids that we need to consider, and that's their size. And size is very important. So we tend to define something as being a colloid if it exhibits the right size, or if it is the right size. And the colloidal domain, or the colloidal regime, extends over quite a wide range of orders of magnitude. So you can see that the colloidal regime begins at about 10 to the minus 9 meters. So proteins are colloidal aggregates or colloidal structures. And if you think, well, proteins really are a collection of amino acids in a polymer chain, but they're not straight polymer chains. They're not a straight chain of amino acids. They coil up into various globular shapes with active sites and important areas within the wider molecular structure. And that coiling up of a long amino acid chain is through forces that are not chemical bonds. They are hydrogen bonds and van der Waals forces that hold and maintain the tertiary structure of the protein. So there is an aggregation of lots of molecules. And the colloidal domain extends right the way up to about 10 to the minus 5 meters. So bacteria are subject to this sort of colloidal domain and act like colloids. They are suspensions of, albeit very complex, particles in solution. So thinking about size then, and if we think about the colloidal domain as something like 1 nanometer to 1 micron, let's first concentrate on size regimes to the left and right of this colloidal domain. Well, to the left, we have the sort of chemist's regime, what I would describe as maybe the organic chemist's regime, or the inorganic chemist's regime. We have molecularly dispersed solutions, we're looking at solution chemistry in which single molecules are zooming around and bombarding with one another and reacting to generate products. And we as chemists think about the properties of the atoms that make up the molecules, and they define the reactivity and the behavior of those molecules. If I have a molecule with a carboxylic acid on a functional group, then I can make certain predictions about the way in which that molecule will behave. To the right of our colloidal regime is the sort of bulk phase, large materials, and of course kinematics applies here, or indeed if we're talking about large crystals, then solid state physics applies. In the middle of this region, from 1 nanometer to around 1 micron, we can apply a consistent set of physical laws to materials within this size range. They're not molecules, but they're not bulk phase materials like large crystals. They are self-assembled aggregates of molecules that behave and act in certain ways. Now, colloidal materials are all composed of at least 2 phases, and this is important. There will be one dispersed phase in a second or a continuous phase. So have a look at the diagram there. The blue circles is my dispersed phase, and the green background there is my continuous phase. So think back to the example that I gave at the start of a nanoparticle. Well, a nanoparticle would be my dispersed phase, and if I've got my nanoparticles in an aqueous suspension, then water would be my continuous phase. Importantly then, you'll note that I don't use the term solubility here. I'm not talking about solubilized phases. If I dissolve sodium chloride in water, then it dissolves and it's hydrated and it becomes a molecularly dispersed solution. But I'm talking about a dispersed phase here within a continuous phase. So it might be that the dispersed phase isn't actually soluble in the continuous phase. But we can change the chemistry of the surface of a particle, for example, to render it evenly dispersed throughout a continuous phase. Now, colloidal systems are found absolutely everywhere. Milk is the classic example of a colloidal system. It's a collection of fat and protein particles suspended in an aqueous continuous phase. Now think there, those fat and protein particles don't necessarily want to be in water, but they're well dispersed within the continuous phase of water and remain stable and don't separate into their constituent phases for very, very long periods of time. And you can see there are lots of other examples. So the detergents that we clean our plates and laundry with, these are all examples of colloids. Paints are often emulsion-based paints, and they are examples of colloids. White paint, for example, is an emulsion based on titanium dioxide particles dispersed in a continuous phase of oil. They're found very, very heavily in the cosmetics industry. So if you think about any creams or hand gels or shampoos, soaps that you use, these are all examples of colloidal materials. Blood is also a colloidal suspension. It's a collection of things like white blood cells and red blood cells, and these are within the colloidal regime, and blood acts as a colloidal suspension of biological matter. When we're describing a colloid, we tend to describe the system based on the continuous phase and the dispersed phase. So for example there, a classic example is the milk example, right? That's an emulsion. That's liquid droplets of fat and protein that are suspended in water. Now those two things don't want to mix, but they do, and they remain stable for a long period of time. Similarly, you can see the example of a paint, for example, which is a type of emulsion, but we'll call it, on there it's written as a sol. It's a dispersion of solid particles in a liquid, an oil continuous phase. Now, just one word of caution here, because I always warn people to be slightly careful with the use of the word phase here. We're using the term phase a little bit more loosely than we would in conventional chemistry. We are using it to loosely describe the physical state of the system. So whether or not it is a solid particle dispersed in a liquid oil is what we're talking about here. We can define the solid phase there, and we can define the dispersed phase. But it's a bit different to our true definition of the term phase. You know, if I was to say, well, something sits in the solid phase or the liquid phase or the gaseous phase, then we'd think that thermodynamic stability had been acquired. I put a block of some water in the freezer, it freezes, and it is transformed into the solid phase, and that's thermodynamically stable at those temperatures. But a lot of colloidal structures don't actually ever achieve thermodynamic equilibrium. Look at one of the examples there being for milk. It's a collection of fatty droplets in water. Now, those two things don't really want to mix. Fat and water really don't want to mix. You know what happens if you mix balsamic vinegar and olive oil to make a salad dressing? You shake it up or you stir it very quickly, but over time, the aqueous phase, the balsamic vinegar, and the oil phase very simply separate into their separate constituent parts, and you have to shake them or mix them again to get a homogeneous salad dressing. That instantly tells you that post-mixing, that system hasn't reached thermodynamic equilibrium. Where colloids are concerned, then, we mix these two things that don't necessarily want to mix, but we can tinker around with their chemistry, so the chemistry of each phase, to prolong the stability of the system. We can allow them to become mixed or stay mixed for long periods of time, even though they're not thermodynamically stable systems. Now, most of these things have identifiable non-equilibrium states. So we have within colloid science things like colloid glasses, creams and gels, and all of these systems are locked into what we call a kinetically trapped state. So they're not thermodynamically stable, but we trap them in a kind of false stability, if you like, that we call this kinetically trapped state. Now, given that these things are inherently thermodynamically unstable, then we want to be able to understand and control the stability of these systems. I.e., for example, if Hellmann's make a mayonnaise, which again is two phases that don't want to mix, it's an emulsion, Hellmann's need to know that that mayonnaise will exist somewhat indefinitely on the shelf, and they have a stable product that they can reliably sell to consumers. So when thinking about this stability and how we might tinker with the chemistry of a system to render it into this sort of kinetically trapped state, I want to develop our understanding of the concept of a timescale within a colloidal system. So let's imagine the timescale from the perspective of a particle, right, which would be our dispersed phase. Let's keep it simple at the moment and think about a dispersion of particles in water, in an aqueous suspension. And let's imagine that we are that spherical particle, a simple spherical particle, doesn't matter what it's made of, it's a collection of molecules. But that particle is moving through solution and it experiences motion through something we call Brownian motion, which is essentially the bombardment of that particle by solvent molecules, which is causing it to move around solution. And that was developed into a formal framework by Einstein. And within that framework, we think about something called the diffusion coefficient, which is a measure, on a simple level, it's a measure of how quickly the particle is moving through solution. To define that diffusion coefficient, we think about a distance over which a particle is moving. So we define that as the mean squared distance, or x squared. And we define a time that it takes for that particle to move a given distance. And that, when you divide that mean squared distance by the time that it takes the particle to move that distance, you get something called the diffusion coefficient. So think back to GCSE physics when we were thinking about speed equals distance over time. It's that kind of relationship. Now, we can calculate the diffusion coefficient for a spherical particle in a dilute solution, and it's given by the ratio of the thermal energy, kBT, which is the temperature multiplied by the Boltzmann constant, and the frictional drag that the particle experiences. So look at the F term there and have a look and see how we calculate the frictional drag. It's related to the viscosity of the solvent. Well, that makes sense because we know that if a solvent is more viscous and it's thicker, then we can expect a particle to move much more slowly through a viscous solvent. And it's related to the particle radius. And we know that all of these particles are subject to Brownian motion. And if the particle radius is larger, then it's going to be bombarded by many more solvent molecules, and we might expect the particle to move much more slowly through solution. If we can combine the equations then for the on the previous two slides, then we set the square of the particle radius to be proportional to the mean squared distance moved, and we start to develop a kind of time scale for a colloid. What we're saying with that equation on the left there is that the time that is taken for a particle to move a certain distance is largely dependent on the particle radius. Makes sense, the bigger the particle, the slower it moves. The solvent viscosity also makes sense. More viscous solvent, the slower a particle will move. And the temperature, well, that's related to the thermal energy, kBT. So the higher the temperature, the higher the energy that the molecules have, and the particles have, and the faster they move. Now that all works very well for a relatively dilute system. It doesn't take into account any gravitational forces, and remember that some of these particles are big enough to experience gravitational forces. It doesn't take into account any mechanical forces or any thermal forces, so any convection forces that the particles might be experiencing. And it doesn't allow for any kind of concentration effect. So you see there's no mention of particle concentration in there. We only talk about the radius, solvent, viscosity, and the temperature. We can expect that if we increase the concentration of particles within our suspension, then particles may now be close enough to start interacting with each other. There may be attractive forces set up between particles, in which case they're going to aggregate and move more slowly. Or there may be repulsive forces between particles, in which case we might expect their speed or their diffusion coefficient to increase. Now, usually within colloid science, and you've only got to think about hand cream, right? We have systems that are far more concentrated than dilute aqueous suspensions. Now we can partly address this by considering just the viscosity of the material in question. So if we have a hand cream, by where the continuous phase might be an oil, the viscosity of that is going to be far higher than an aqueous suspension. So we would substitute here the viscosity for the continuous phase under study. And the differences between the time it takes for a particle to move a certain distance in these systems can be very, very large. Think about an emulsion such as a hand cream. The viscosity in that system can be 1,000,000 times that of water. Now think of the impact that that has on the movement of particles within that particular emulsion system. That goes some way to explaining what we mean by the term kinetically trapped state. When you look at those equations, particularly the one on the bottom there, where we're talking about an increase in solvent viscosity, if I've got an emulsion, such as a hand cream, for example, which might consist of aqueous droplets suspended in an oil phase. Now, common sense dictates that the aqueous phase and the oil phase will want to separate over time because thermodynamically they don't want to mix. Firstly, let's consider what has to happen in order for them to phase separate. Well, the emulsion droplets have got to collide and come together for water to mix with water and oil to mix with oil, and eventually they will phase separate. And this is why time is so important in these systems, because what we're saying is that the time that it takes for a droplet to move some mean squared distance in this system is very, very long. And if it's very, very long and the particles are moving very, very slowly, then it goes some way to explaining why these systems are kinetically trapped in a seemingly stable state and why they don't phase separate very rapidly. Now, when these systems were being investigated towards the end of the 19th and the start of the 20th century, of course, a lot of them were on the kind of nano-sized regime, and it was very difficult to study them. In 1903, then, the development of the ultramicroscope occurred, and suddenly it became much more simple to visualize these systems, but indeed confirm the existence of individual particles. Okay, so for the second part of this lecture, I just want to, by means of an introduction, I want to go over some of the basic definitions that we have in colloid science, because again, we think about things in slightly different ways. So let's first of all think about how we define concentration. In colloid science, it's most appropriately recorded in two forms. You can have the number density, which is the number of particles per unit volume, or you can have the fraction of the volume of the system that's occupied by your particles, so the volume fraction. So you can see there that that's the volume of a sphere, and it gives us an idea of the total volume of the system that is occupied by the particles under study. So we're not talking about moles, and in this slide we're not talking about mass, we're talking about either the number of particles or the volume of particles in our system. And we tend to prepare these systems in terms of weight or volume. Now, when we talk about the size of colloidal systems, we often refer to the diameter of a particle as opposed to its radius. And because these are pretty complex systems, they tend to show something called polydispersity. So that means they have a spread of sizes in any one given system. Now these systems can be monomodal, so they can have a well-defined mean particle size, but a spread of particle sizes around a modal value. Or you can get multimodal distributions of particles. So you might see two modes. We also define the interfacial area in a colloidal system. So again, let's think about a simple suspension of spherical particles in water, for example. There is an interface between the solid particles and the water phase. So there is an interfacial area. So we define two types of interfacial area. We can think about the total area in suspension. We know the concentration, we know the volume of a particle. We can calculate the total area in suspension. Or we think about the area per unit volume of sample. So the total interfacial area on a particle on a suspension of particles per mil, for example. And the areas involved, the interfacial areas, the surface area of these particles, if you like, can be absolutely massive. So let's consider just 1 litre of a colloid with a suspended particle that has a diameter of 100 nanometers and a volume fraction of 0.1. So the total volume occupied within that suspension by particles is 0.1. The total interfacial area on those solid particles can be, it is 6,000 meters squared. And that's that area is approximately equivalent to the size of a football pitch. And it's important to remember that the area, that interfacial area, is really important. You can't have a colloid without an interface. And if we've got a dispersion of particles that want to aggregate and phase separate, so all the solid wants to clump together, then that interfacial area is going to be really important because we can start to play around with the chemistry of the surface of our particles and stop them from aggregating and stabilize our colloidal suspension. We also define something called effective concentration, and we will think about this in much more detail as we go through the course, but I'm going to very briefly introduce it here. We know that we can get a number density of particles in a suspension. We can calculate the number of particles per unit volume, for example. And we know that over time, particles will start to aggregate. Sometimes it might be necessary for us to absorb large polymers on the surface of our particles, for example, to create some kind of steric stabilization and stop them from aggregating. Of course, when we do that, the number density of the particles remains unchanged. We don't change the number of particles per unit of volume. But the presence of those adsorbed layers increases the effective volume and the volume fraction of the particles. So if we do that, then we have to consider the thickness of the adsorbed layer and modify our volume of system that is occupied by the particles. So we call that an effective concentration. Okay, so we've kind of looked at the history of colloids. We've defined what a colloid is. We've considered time in these systems. And I just finally want to consider what we mean by stability in colloidal systems. And hopefully this lecture will set us up well for the rest of the course. The term stability then should be used in context here. Colloidal stability relates to the physical state of the system. So if I've got my emulsion, and let's imagine it's a milk, for example, consisting of a fatty sort of protein liquid liquid droplets that are dispersed in water. So my particles are the fatty droplets and my continuous phase is water. If those droplets remain well dispersed throughout the system, then we consider the colloid to be stable. But if those fatty droplets start aggregating together and I start to get a separation of fat and water, or oil and water, then the system is no longer stable. And there are a couple of ways in which the system can become unstable. And of course, when we're talking about an unstable colloidal system, we mean that particles or droplets will start to aggregate. And if those particles or droplets start to aggregate and the forces that hold the particles together are very strong, then we term that permanent aggregation or coagulation. And a good example of that is in cheese making, when whey forms on the top of the colloid. That's just protein that's been coagulated, and that's been coagulated by imposed chemical changes. So here's an example of where we actually want to induce instability in the system as opposed to maintain stability. Flocculation then is a much weaker form of aggregation, and it often involves electrostatic forces, and it's entirely reversible. So if I just shake the system again, for example, or I stir it again, then I can render the system stable once more. And precipitation then is a complete phase change to a solid from a molecularly dispersed system. So we're talking about something precipitating out of solution here. We'll talk in much more detail about these as we go through the course. And things can also sediment or cream. So some of these particles are just large enough to be subject to gravity. And if the particle is more dense than the continuous phase, then they'll sediment to the bottom. But if the particle is less dense than the continuous phase, then they'll just cream to the top. Okay, so colloids have a very rich history. They're very important from a commercial and industrial perspective. There are lots of different colloids around, and we'll look at lots throughout the course. Time is very important for these systems. We looked at some basic definitions, so concentration, interfacial area, and effective concentration. And we talked about stability, so we spoke about what stability means in terms of a colloid, and we looked at different ways in which systems can become unstable or phase separate.